بسم الله الرحمن الرحيم والصلاة والسلام على أشرف المرسلين سيدنا محمد وعلى آله وصحبه أجمعين. Assalamu alaikum everyone. Okay, so we're going to be continuing with what we discussed on Sunday with Lyapunov's direct method. So let's start with the recap. So we looked at state space models. So since we started topic number 4, when we talk about the stability and control of mechanical systems, we transformed. We are considering systems of this form, right? So state space models that are nonlinear ordinary differential equations of the form x dot equal f of x plus g of x multiplied by u. So u here appears linearly in the dynamics. However, x, the function can be f of x and g of x can be nonlinear functions of x, similar for the y, which is the output. And there's a special case of this, okay, that you have the f of x is just a linear matrix and g of x is just a constant matrix. Then this is, this linear state space model that you should be all familiar with. When we wrote mechanical systems into this state space form, we found that usually the state is a position-like variable and velocity-like variable. Okay, and then this is usually a recurrent theme. You always have theta, psi and psi dot, theta and theta dot, q and q dot, and so on and so forth. When we went, if you look at satellites and, for example, something that lives on SO3, then it will be something in SO3 as the configuration, and the velocity will be something like r dot or isomorphic to r dot, which in this case is just the angular velocity. If we go to something that lives on SE3, it's okay. Also configure the other state will be something isomorphic to h dot, which is the twist, and so on and so forth. And we said that usually the state space in these systems is the tangent bundle. Or the cotangent bundle. As you know, we can also write, instead of positions and velocities, we can write them in positions and momenta. Okay. Then we looked at the nature, the geometric nature of this dynamic system, x dot equal to f of x, when we have now a function of time. So actually the evolution, okay, because we have a differential equation, so this x dot is actually a differentiation with respect to time, which means that the x is a function of time. And in the Euclidean case, this f, you think of it as just something that eats a vector in Rn and gives you back another vector in Rn. However, the correct geometric picture is that it eats a point on the manifold. For every one of these points, it will give you a vector field that lives in the tangent space to that point on the manifold. And we said that the solutions of, and we said that f of x, in this way, defines a vector field. So a vector field is simply a vector at every point, but on all points on the manifold. And then we said the solution of the dynamical systems are usually given by the integral curves of this vector field. So the vector field corresponding to f, we call it sigma f. Okay? There was a formal definition of what the vector field is in the slide. You can just read it, but the intuitive way is the intuition of just what a vector field is all what you need to understand. Then we said that if we're given the dynamic systems without even solving, trying to solve for this numerical solutions, for the solutions of the dynamical system, we can simply identify the equilibrium points as the points that all of the points on the manifold that would satisfy f is equal to 0. Okay, so when you plug in these equilibrium points, you get that the value of the function is 0, and equivalently, if f is 0, then what else is 0? The x dot, the tangent vector there is 0, which means that if you start at that point, you always stay there. Okay. Yes?
If the point is 0, can't it be also sloped? Why does it have to be the tangent vector equal to 0? You get me? If you have a parabola, it doesn't have to be on the 0 point. It can be beneath it.
No, what we're talking here about is the dynamic itself. X dot is equal to f of x. Not the function of x. We're not talking about a scalar function like what we do in Lyapunov. That's another thing. So f here will give you a tangent vector. Okay. So x1 dot and x2 dot and x3 dot.
So f here is that tangent vector.
F, exactly, it's the tangent vector. Yeah.
Not the point.
No, it's not a point. It's a. If you write it in components, it will be a vector in the end. Okay. So. And then when we look at these equilibrium points, they can be, we can study their stability. And by stability, we mean that how do the system, the integral curves behave around it. Okay? And by integral curves are the solutions of the dynamical system. So if we start near a point and we remain near it, then we call this a stable point. If we start near a point and then we diverge away from it, we call it an unstable. If we start near it in a small region, then we converge to that point, we call it asymptotically stable locally. And if we can start anywhere in the state space and then we can converge to that point, we call this point globally asymptotically stable. Last time we had different examples. We had looked at the pendulum example as a mechanical system, and we're going to come back to that mechanical system later on. Then we looked at Lyapunov's method. We said that, is there a way that we can identify, instead of just plotting how the system will evolve, like what we did with the phase portrait of the pendulum last time, can we just take the f of x and try to analyze its properties, and then we can identify whether the point is stable or not? And we said yes, that's the whole idea of Lyapunov's work. And there are two main big work that he did, the indirect method and the direct method. The indirect method is simply take the f of x, linearize it around this equilibrium point, okay, and then by computing the Jacobian and then evaluating the point, and then looking at the eigenvalues of this matrix, okay. And then from this eigenvalue you can identify the local asymptotic properties, the local asymptotic stability or the instability of that point. The indirect method was only mentioned in the slides for your information. It's not included in the exams and so on. But even, by the way, it's really very easy, okay, to actually work with. You're gonna have, inshallah, some practice problems for it at home if you really want to, just to solidify your understanding of it. But it's very easy in implementation. The direct method is the one that that we're going to be focusing on and using later for assessing the stability of the systems we're going to be looking at. And the whole idea is that, so the idea of Lyapunov is that he thought of, what, why don't we choose something like energy, which is a function that eats a point on the manifold and gives me a scalar. So it's a scalar function on the manifold, and it is smooth and so on. So I assume everything is smooth. And then we can examine its time variation, and by looking at how v dot changes, we can actually deduce some stuff about the system itself. And then Lyapunov's direct method, simply you can summarize it as the following. So given the x dot equal f of x, and there is an equilibrium point you want to study its stability, so you have to choose already one of the equilibrium points. You cannot talk about stability of the whole system. There's no such thing, because you have every system. In general, nonlinear systems might have multiple equilibrium points. We have to study the stability of each one separately. So x star is called if x star is an equilibrium point of the system, we say it's stable if you can find a Lyapunov function v of x if you can find a Lyapunov function such that when you plug in this x star, you get 0. So it's the value of the function is 0 there, and away from this equilibrium point, you have it's positive. Okay? And these two conditions together, they are called positive definite. So you call that this function is positive definite. Sorry. Okay. So you say that the function is positive definite v, and then you evaluate v dot, and you cannot evaluate v dot except using x dot equal f of x, and as we're going to be seeing today. So you evaluate the time derivative of this function along the trajectories of the system, and then you must show that this is always less than or equal 0. And by less than or equal 0 here, then this is negative semi-definite. If you can have the same criteria, but you have a stricter condition that it's not just, you can show not just negative semi-definiteness of v dot, you can also show it's negative definite, you can conclude it is locally asymptotically stable. If you want to go to the stronger criteria, that it's actually globally asymptotically stable, you have to add one extra condition on these three, that the v goes to infinity as you move away from this equilibrium point in all directions. Okay? I just have to, I move this way and that way and so on and so on. Okay? And this is written this way. Actually, we're assuming that x here is in Rn because we have this minus, but you can generalize this on a manifold with proper terminology. Okay? But the intuition is exactly the same. You just move away from the equilibrium point. Today we're going to have, inshallah, a lot of examples on this implementation. And then we stopped at, a little bit about what do we mean actually by a positive definite function. And we said that a positive definite function, I just showed you some pictures, and then we came to this formal definition. So this is what we're going to be doing today, and we're going to extend it a little bit. So the formal definition of what a positive definite function is. So a function psi that eats x and gives you r. So it's a function, it's a scalar function. It eats a point on the manifold, gives you a real number. we say it's locally positive definite about an equilibrium point if you evaluate the function at the point and you get 0, and you can find a neighborhood that includes this equilibrium point such that the function is positive, okay, in this equilibrium point. Okay, so except at the point itself. So sorry, it's the function is positive in the neighborhood of this equilibrium point, except at the equilibrium point itself, because at the equilibrium point we really want it to be 0. Okay, so it's 0 at the equilibrium point and positive everywhere else. So this is the formal definition. Last time I showed you some figures in 1D and 2D, but these are only limited to just to visualization. This is how you can check it analytically, okay, for in general. And today we're going to be applying this definition in some examples, inshallah. We say if you cannot just show it's positive definite, but it's positive semi-definite, which means that it's greater than or equal 0, then this is the semi-definiteness. And it is globally, if you can show it for all, not just for some neighborhood, but for all of the state space, again, except the equilibrium point we're talking about. And then we say the function psi is locally negative definite or negative semi-definite if you can show that its minus is positive definite or positive semi-definite. So in case you haven't seen this way of writing it, so this actually point is actually 2 in 1. Okay? But this is it's a very compact way of writing it. So you can read it as follows. So psi is a map that goes from x to r, is locally negative. Remove this part because it's in a bracket. Okay, so you can just you can read without it. It's negative definite if minus psi of x is locally positive, and also remove the bracket, positive definite. Okay, so it's negative definite if the minus of it is positive definite. Makes sense, right? Okay, but if you want to show that it's negative semi-definite, then you must show that it's positive semi-definite. So this is what the bracket means. Okay, just linguistically. So instead of adding one extra condition that is exactly the same, you can just write it compactly like this. Okay, make sense? Okay. Yes. Any questions? This is only the formal definition. We haven't talked about any recipe of actually evaluating whether the function is positive definite or negative. So that's what we're going to be doing today. X star, this equilibrium point, is actually a strict local minimum of psi. Okay, and if you remember from just your calculus courses, that if psi is a differentiable function and psi and the x star is a local minimum, then the gradient must vanish there. Okay? So the reason actually it's 0, if you evaluate the function at 0 and it's positive everywhere, it means that it's like some sort of exactly it's a local minimum, and if it's a local minimum, it means that the tangent added is 0. Exactly. So the tangent to this curve is at 0. If you generalize this to n dimensions, you can do this with the Jacobian. Okay? So the Jacobian actually of this function, okay, should be exactly equal to 0. And you see, so we have two conditions now for these equilibrium points. The function at it is 0, but what else? The gradient of the function at this point is also 0. An equilibrium, if you have a point on the manifold that satisfies both of these conditions, we actually call it a critical 0, not just a 0 of the function or an equilibrium point of the function. We call it a critical 0 because the value of it is 0 and also the gradient of it is 0. Okay. Why is this important? You're going to be seeing now next. This is actually just the figure. Okay, so this figure here shows, okay, if you have this positive definite function and this is, okay, it's locally positive definite around this point, you see it's clearly the function, the value of it is 0 at the point. So this is, this is the 0. Sorry. So this is the 0, and you see it's actually also the gradient of it. You'll find it's constant. Okay.
This is positive definite.
Sorry.
This is positive definite, right?
This is locally positive definite. Yes.
Can you show us a local semi-definite, positive semi-definite?
Semi-definite as a figure. Let's see. So at these 2 points, for example, it will be 0. So it's not only 0 at one point, it's actually 0 about like a plane, yeah, something, you know, like more than 1 point, exactly. Okay?
I get you, yeah.
Okay. There's another closely related definition you definitely heard about, which is positive definite matrices, right? Have you heard about positive definite matrices, negative definite matrices, and so on? So what's the difference between these two? So a real symmetric matrix, it has to be real and symmetric. A, you can, by the way, you can even generalize it, but just stick for now, for time's sake, that it's a real and symmetric matrix. And by n, we say it's positive definite matrix if you can multiply it before and after by some vector, and it's always 0. It's always greater than 0, sorry. It's always greater than 0, and this is valid for all vectors in Rn except the one that's 0, the 0 vector. So it's only when I plug in here x to be 0, I get the value equal to 0. But if I plot any other vector, in Rn, I should always get a positive value. If that's the case, we say that it's positive definite matrix. We say about A is positive definite matrix. Make sense? If it's greater than or equal 0, positive semi-definite. If it's less than 0, negative definite. Less than or equal 0, negative semi-definite. Make sense? Okay? The way we usually write that a matrix is positive definite or positive semi-definite or negative definite or negative semi-definite is usually using this symbol. These are not the same symbols.
If it equals 0, how can we differentiate between if it's a positive semi-definite or a negative semi-definite?
Sorry, again, could you repeat the question?
If it's 0.
What is 0?
X transpose AX equals 0.
Is equal 0, exactly.
How can we differentiate if it's a positive semi-definite or a negative semi-definite?
So is it equal 0 at some point different from the origin? At some vector different from the origin?
Let's say yes.
Okay, then it's automatically positive semi-definite. Okay, so by the way, so here you check all points, all vectors. Okay? If you have, okay, so I think I get your point. If it's sometimes positive, sometimes negative, I think that's what you mean, right?
No, what he says is we have a condition that when we plug, except for the 0 vector,
Yeah?
when we are checking for all the other vectors,
Yes?
if it is greater than 0 or equal to 0, then it is positive semi-definite.
That's right.
If it is less than or equal to 0, it is negative semi-definite.
Absolutely.
So the question is, if it is equal to 0,
Okay, I see.
then how can we say it is positive or semi-definite?
That's an excellent question. And you should, if you think about it for 1 minute, I think you can get it. So that's a smart question. So I'll ask it. What do you call a matrix? Let's say that I have another matrix here, I call it J. And I multiply before and after x transpose J x. And I find it's always equal to 0 for all vectors. What do we call this matrix J?
0 matrix.
No.
A 0 matrix?
What do we call this matrix J?
Nullity? Null matrix? Okay.
No. I'll repeat the question again. If I have a matrix J, and I pre-multiply it and post-multiply it by x in this way.
Okay.
So I make x transpose Jx. And I can show it's always equal to 0 for all values of x. What do we call this matrix?
Additive identity?
The answer is skew-symmetric. A skew-symmetric matrix is the one that satisfies x transpose J, x is exactly equal to 0. And that's why you see I already excluded it in the definition here. This case you can never have it, because a symmetric matrix, by definition, will never be equal to 0 for all values of x. Okay?
Doctor, do you mean the X itself is a skew-symmetric or the A?
No, the matrix.
The A.
Yeah, the A itself. X here is an unknown. It's an independent variable. You can be anything. You see, that's why we say it's for all x. Okay?
So by extension, okay, I understand.
Any questions? Okay.
I think
So-
just one point,
Yep.
just to answer the question, whoever had it, the negative semi-definite is it can be sometimes 0, but other times it will have to be positive or negative.
That's right.
It cannot be 0 at all times. So
Yeah.
if it is negative and 0, it is negative semi-definite, positive and 0, it is positive.
What if it's positive, 0, and negative?
It's inconclusive.
We call it indefinite. Okay, we cannot say anything about it. Okay? I cannot say it's positive. I cannot say it's negative. It can be anything. Okay, so that's the most general case. If you want, if you have a matrix that satisfies this condition, and I just want to say that A is positive definite, usually we use this symbol. Okay, I say, by the way, this is not the same. Okay, you have to look very closely. You see, it's like a little bit of curly greater than. This is a curly greater than or equal. This is like a curly, so it has some sort of
Premium mathematics symbol.
It's available. It's even in Microsoft. Okay, so it's available. Okay, so this is really I even forgot its name, by the way. But okay, this is really basic mathematics. So this symbol is for functions. This symbol is for matrices. Is there a way that you can actually check, if I give you only the matrix, whether it's positive definite or negative and so on and so forth? Yes, the eigenvalues. Okay? So the eigenvalues are already equivalent. Okay? You can identify from them how this matrix behaves. So if you have a greater than 0, so this positive definite matrix, it has to have all eigenvalues greater than 0. Greater than or equal means that, which means the eigenvalues could be non-negative. So zeros or positive. Negative, less than, only negative eigenvalues, and less than or equal, 0 or negative. Okay? Make sense? What? So you might think we drifted, right? So why are we talking about all of this? Take a look at this theorem, okay? You all know a Taylor series expansion? Okay? So I'm going to show you this theorem only for the case of Rn. However, you can generalize it for a manifold, but I'm not going to do that for time's sake, okay? So imagine that you have the state space to be Rn. So your favorite usual. I hope it's not anymore after the course. But if you have an Rn and you have a function v that eats Rn and gives you R, and you want to check whether it's positive definite around some equilibrium point. If we expand this function out with Taylor series around this equilibrium point, and we do it only for second order. So we have that v of x is equal to v of x star plus the first derivative, which is the Jacobian, right, multiplied by the difference from the point x and this equilibrium point, plus half of the distance again, but transposed, and the distance here, and you multiply here by a matrix. Does anyone know what this matrix is called? The Hessian, exactly. Inside of this Hessian, okay, first of all, it will be an n by n matrix. And if you look inside of it, you'll find what? Second derivatives, exactly. So here, this is a matrix of first derivatives. The Jacobian is always partial v by partial x1, partial v by partial x2, and so on. So here, this is how you build up this matrix. And this matrix, you build it by second derivative and so on. Okay, so second derivative with respect to xi and xj. Okay. This v, if it's a function, if we're thinking about, we want to check positive definiteness, and we say that x star is at equilibrium point, then we know that v of x star should be 0.
Okay.
And also the gradient of it, the Jacobian of it, should also be 0. So you can actually conclude that if we're checking the positive definiteness around the critical 0, then the function will be locally approximated by something that looks like this. Okay? So you see, it's half some vector transposed multiplied by a matrix with another vector.
What is V over here?
V is the function you want to check its positive definiteness.
So it is that energy-like function.
The energy-like function, or its derivative. Remember, when we do Lyapunov's method, we have to check whether V is positive definite. We have to check the definiteness of the function, but we also have to check the definiteness of its derivative. So in both cases, you just, you want to always check the definiteness of the function.
So this is sort of a shortcut for that.
Absolutely. So now the conclusion, exactly. So this is actually a check whether, if you really want to check if something is locally positive definite, you can simply calculate its Hessian, and you can look at the eigenvalues of the Hessian, and then you can conclude from that whether it's locally positive definite or it can also be
Negative.
negative, exactly. If I have here, this is to be negative definite, I can also conclude this is negative definite. If I conclude this is, if I have here eigenvalues that are 0, I can conclude this is positive semi-definite or negative semi-definite. Okay? So it's very easy to actually check just by looking at the hashing. Okay? Can I conclude this is globally?
No.
Why?
Because we are talking about the neighborhood of the equilibrium point.
You can, if you can limit x to infinity.
If this
And
x
still-
x is the range around which we are checking, beyond that x value,
Is V equal to this expression?
No.
It's approximately, exactly. We remember what we did here. We did Taylor series.
Yeah.
And then we excluded higher order terms. So if I fail actually to use this, it doesn't mean that the function is still,
maybe higher powers might contribute.
exactly. The higher powers already contribute and make it maybe maybe it's locally, positive definite, but away from it, you cannot actually guarantee it's still gonna stay positive definite and
And
so
the
on.
limit is going to be the value of x, right? From the value that we're using, x minus x star.
So
So this is-
locally, when you say locally, you're not saying how big or small the region is.
Isn't this x the magnitude of that region or length of that region for which we are checking?
We're not going to go there. Yeah, that's right. You're absolutely right. You can characterize, but this is not the whole point. When you say it's locally in the end, you cannot, it's just like, this is the region where, you have a proof that there's a region where this is true. How big or how small is it, that's a completely different story. Okay?
But then how this choice of x is going to matter?
The x is the function. Sorry, the x is the variable. It's not a choice, actually.
Then x star?
X star is the equilibrium point. You want to check positive definiteness around. So it's a given, right? And it has to be an equilibrium point. So it's not a choice. Remember? So you have to check, for example.
But they can multiple equilibrium.
Absolutely. But now you can check for different values. Okay? And that's why when you evaluate, you see here, when you evaluate the Jacobian, you evaluate it at the equilibrium point. So I might evaluate it, the Jacobian will always be 0. However, the Hessian, when I evaluate it at the equilibrium point, sometimes it can be positive, sometimes it can be negative. Okay? So, are you satisfied with how, so now we're going to be seeing later, inshallah, let's see. Yeah, inshallah, we have time to actually do some checks. So given some functions on, Rn, and maybe we're going to try some manifolds today, something that's not Rn, and we see actually how we can check its positive definiteness. So we're going to have some more examples, but that's it. This is all about definiteness. Now let's go back to computing V dot. We said that the whole idea of Lyapunov is that choose a function, calculate the time derivative of that function, and check the definiteness of both. So how do we compute even V dot? If you took a nonlinear dynamics course and nonlinear analysis course, you already tried it out, and if you actually choose this function easy, it becomes really trivial. But what is the real, the geometric picture in general? If I have a manifold where x, so the state space here is a manifold, and I'm looking that this is the trajectory of, of the system, starting from some initial condition. At every point, I have xt, so xt is the point along the solution. Yes, no.
Sorry, one thing. Previous, yeah, the positive definite Hessian gives a sufficient not necessary condition. Can you explain this?
Which means that if you can show the definiteness here, of the positive definiteness of this one, this means already the function is locally positive definite. However, if it has zeros here, you cannot conclude, okay? You cannot say that the function is not positive definite. So that means that it's sufficient, but not necessarily. Because exactly the point you mentioned, that the higher order terms can actually make it positive definite. While this term can only show positive semi-definiteness. That's the idea.
This works that way with that way.
Exactly. Yeah. One condition. So this is positive. If this is positive definite, you can conclude it implies that the function is locally positive definite. If this is positive semi-definite,
don't know.
you cannot say that this is not positive definite, because the higher order terms can make it positive definite.
Okay.
That's what it means.
So
Okay.
it's either semi-definite or definite. It can't be negative.
Exactly. Yeah, absolutely. I cannot be negative, but you already checked that. Exactly. So at least you've guaranteed that it's positive definite. And then we go back to the same idea. I can choose the function and I can get some stability results from it, and you can choose another function, you can get another result. So that's the same idea. Okay. So now x is a point on the manifold at time t. X dot is the tangent vector of the dynamics. So, and we have that x dot is equal to some function of x, okay, given by the dynamics. For any smooth function, and you see here it has to be smooth. So everything is smooth. You have a smooth manifold. We have smooth, atlas, and all of that stuff that we discussed a long time ago. So we have a smooth function on the manifold. If you want to calculate its time derivative as a function of x at some time t, it is given by the pairing of two things. dv as a function of xt, and the pairing with x dot. And you know that x dot is given by the dynamic f of x, so it's actually the pairing of these two things. What is this bracket here? This bracket, first of all, what is the dv of x? It's something that lives where? In the cotangent space, which means that it is what? It's a covector. So this is a covector. And what about this bracket? First of all, x dot was what?
Tangent vector.
Was a vector in a tangent space.
Not a tangent space, yes.
Was a vector in this red tangent space. And for every vector space, there is what? There is a dual vector space, and we call this the cotangent space.
Okay.
And this is a covector. It's a special type of it's a special covector there. And what happens when I combine a vector and a covector? What do I always get?
Feed on the feed.
A real number.
Real number on the feed.
Okay. So this bracket here, so this duality product, is simply will eat one covector, and will eat the vector and gives you a real number. That's it. What we call this dv of x, we call it the differential of the scalar function. So now, in order to calculate the v dot, I should compute the differential of the function v and evaluate it at the point x, and then I pair it with f of xt. Yeah? Make sense? Is it clear what you're going to be doing? Not at all, right? This is just a abstract definition. It's I didn't tell you anything about it because I did not tell you what the manifold we're talking about. This is very general. Okay? So very general manifold, very general function. So just very abstract definition. Yes.
Can you visualize V on the same manifold so we get an idea? How will
V is a function of the manifold, which means that you give it this point, it gives you one number.
Yeah, of course.
And you give it this point, you give it one number. That's it.
The trajectory of the function. So I can.
This is the trajectory of the function, the blue one.
The trajectory of the state space. That's what I understood.
The V dot.
Yeah.
The V dot is a scalar. You give it this point, it gives you a number.
Yes.
You give it this point, it gives you another number. That's it.
Will the trajectory of the V be on top of the trajectory of the state space when it moves?
You can think of it this way.
Will it diverge somewhere? Or
So you see this blue curve?
yeah.
It's a bunch of points already defined on the state space, right?
Yeah.
If I take all of these points there and I plug in the V, what do I get? You get just a function, right? As a function of time.
Can you say it's some manifold?
No. It's a real function.
Okay.
It's just a function in time. So let me actually plot it. So to answer your question, this is time.
Yeah.
Okay. So at time equal to 0, I'm talking about this point. Time equal to last one, I'm talking about that point. So for every time instant, I can just for every time, I have an xt.
Yeah.
Do you remember what was this called? This actually was called the curve, right?
Yes.
The curve on the manifold. I give it time and I get a point on the manifold. After I get this point on the manifold, I plug it in
To the function.
the V. So the V will eat up the xt and give you
Point.
V of xt. What is V of xt?
Some other thing.
So I'm going to be calling V of xt here just something like, this.
Hell.
It's a function of time, right?
Okay.
Because x is a function of time, so v eats the x, and x itself is a function of time.
Okay.
So then v now is actually a function of time. What is v dot?
The tangent of this.
The derivative of this function
Yes.
with respect to time.
Yeah.
So if this function, I know, let's say for example this function was a sine, this would be a cosine. If this was, a ramp function, this would be just a constant and so on.
Can you say V now is a manifold somehow?
No, v is a function.
Can you turn it into manifold?
It's a function.
Oh, I understand you.
Okay.
But you can't. Yeah.
It's what is it a set?
It's a set, of course.
A function is a function a set? No, you have to go back to lecture 2. Okay? So no, don't confuse yourself. Okay? So so this is the definition of how you calculate v dot. Now let's take the easy case of Rn. Okay? So in case that the manifold is Rn, then v dot is equal to the general definition still holds, dv of x paired with x dot. But this pairing now, if you have Rn, if x dot is a vector, is a column vector, then dv of x would be a row vector. How does this row vector look like? It looks like this. Rings the bell?
The Jacobian transpose.
It's not the Jacobian. The Jacobian is usually the Jacobian of a matrix. What do you call this?
Laplace.
You actually know it in another fashion, actually. You don't know it like this. Usually you know it like this. What do you call this? The gradient of the function. The gradient of the function. What is the gradient of the function? I give you a function, you take the partial derivative with respect to x1, partial derivative with respect to x2, and so on, and you just make them into a vector.
Isn't Laplacian the same?
Laplacian is different, no. It's different, no, something else. I think the Laplacian is related to the Hessian.
And what about nothing else?
Okay? So you see, what do we have here? We actually have two things, of the same nature, of different nature. They are the same thing, but represented in different things. So the differential and the gradient are simply just dual to one another. The differential here is the row vector version of the gradient. And the v dot, usually when you write in terms of the gradient, you usually write this expression, right? It's a vector transposed multiplied by f of x. Why multiplied by f of x? Because it's the x dot, right? So if you go back here, so now if you go in terms of the differential, the dv is given by this row vector, while the x dot equal to f of x is actually given by this column vector. And now if I take this row vector multiplied by this column vector, what do I get? A scalar number. Okay, so this scalar number looks like this. Right? It's partial v by partial x1 multiplied by x1 dot, where x1 dot is f1 of x, plus partial v by partial x2 multiplied by x2 dot, where x2 dot is the second function, and so on and so forth. I can simply write it, in this summation like this.
V dot is, what is the difference between V dot and gradient of V?
The v dot is a scalar function.
But the gradient of a
The gradient, is it a vector or a covector? Now that's the question.
gradient is like gradient of any vector is a scalar, gives a scalar result.
Now you're talking about something completely different. Now you're talking about the gradient of a scalar is a vector.
Gradient of here V is a vector, right?
V is a capital V is a scalar function. It's like the Lyapunov function. So V of x is a function.
Okay.
It's a scalar, and V dot is another scalar. The time derivative of this.
Yes, both are scalar.
Both are scalars. And the gradient of this scalar function is a vector. But when I say a vector here, do I mean it's a vector that belongs to a vector space? Or because just I write it in terms of an n-tuple?
It's a tuple.
It's just a tuple, so you can write it this way or that way. So what is the nature of it? Is it a vector or a covector? Naturally, it's a covector. Okay? If you transform it, if you change coordinates, it will change coordinates as a covector, not the same way as the x dot. The x dot is truly a vector, while this is a covector. Okay? This is very important because we're going to come back to that later when you start to do control, and you'll see why later. But for now, writing it like this or like this is, it's very easy, okay? Because it's just the n-tuple, and whether you put the transpose or not, it doesn't matter. This is exactly the same formula if you go back when we talked about a covector alpha eating a vector v. It was the components, it was the matrix representation of the alpha, right? And then you transpose it, you multiply by the matrix representation of the v. Go back to this slide, I don't remember in which lecture. You're going to find this is very similar. And by the way, in that lecture also we mentioned something about the gradient of a function there. And we said that it was a covector, but this is so just a repetition of what we said earlier. Okay. That's it. So done. So now, to implement Lyapunov's method, to try it out, choose a v. You know how to check its positive definite. Calculate the v dot along the trajectories of the system. You have the system already, so you already have the equilibrium point that you want to check. You already did all of that steps. And you just should check v dot is less than 0 or less than equal 0, and then you can conclude stability and full stop. That's it.
We had 3 stages of that Lyapunov. First one, second one, third one. Like
Yes. Stable, asymptotically stable, globally asymptotically stable. Yes.
if, let's say, one phase.
Yes.
One phase, then can we go for the same function for stage 2? Or
No.
we would have to choose another function?
For example, if you cannot show stability, the other criteria were stronger. So for example, if I choose a function and I cannot show its positive, I cannot even show its positive semi-definite. Can I show its positive definite? It's actually a requirement of it. For a function to be positive definite, it has to be positive semi-definite first.
So this way we cannot go.
No.
And this way.
Yes, you can go. So you can show first its positive semi-definite, and then you can show its positive definite, but maybe not using the same theorem. And that's exactly what we're going to be doing next time. That's exactly what we're going to be doing next time. We're doing something called Lassalle's invariance principle. Lassalle's invariance principle, next lecture, inshallah. Okay? We'll come back. That's an excellent question. We're going to come back to it later. So we're going to go to the board and just, spend the rest of the time until, until you drain out of, mental power. So let me go to the whiteboard.
What if we say we are already drained of the mental power now?
No, that doesn't count. Sorry. I'll start counting from now.
Don't even give that option.
Yes, not an option. Yes, absolutely. Okay. Let's see. Want the blackboard? Let's move this. Okay. So we're gonna start with your favorite case first, which is Rn. Okay. Let's choose some examples. Okay. So this is this is part A, part I. Okay. And then we have multiple examples. Let's take the first example. So the first set of exercises I'm gonna give you some V's. I'm gonna ask you whether they are positive definite or not. Easy. Okay. So assume that we have x equal to x1 and x2, and the function that I'm checking that is half x1 squared plus half x2 squared. Okay. So I want to check whether this function is positive definite or not. Okay. Of course, you imagine it now. This is yes, of course. You say yes, of course, it's positive definite. Why? You already imagine it what? Yeah, it's like the parabola, right? But let's try to use the tools that we did, right? Analytically, not just graphically, okay? So let's calculate the dv of x. Okay, what do you get? First of all, which equilibrium point we actually want to check its positive definiteness around? 0. The 0, 0, right? So let's check, let's say that we're interested in the x star equal to 0. And when I say x star is equal to 0, I mean x1 is 0 and x2 is 0, right? So this is actually equal to, both have to be 0, okay? So that's the equilibrium point. So what is dv of x? It was the covector, which is partial v by partial x1. And by the way, always remember this, golden rule. Partial v by partial x1 is a function of?
X2.
No, all of the x's. It's not just a function of x1. It's a function of all of the x's, okay?
If it was just x1, then we would write d of x over.
We will not, even though that's correct, mathematically that's correct, but we're not going to make this distinction. So I'll just, it's always going to be written like this. So this is in general what you have. So what is this partial derivative? How does it look like here? 2x1? x1 plus x2.
No, wouldn't. Okay.
Any doubts? That's the easiest one, okay? And what about this one? Your favorite gradient, how do you write it? You just say, okay, it's x1 and x2. Does it really matter? No. Okay. Does this make it into a vector?
No.
You see, so alhamdulillah. So now you see, okay, now you're insensitive to this. Writing it like this, writing that doesn't matter. The nature of it is something completely different. Okay. So now let's look at the Hessian. How does the Hessian of this function look like? So the Hessian of v as a function of x. How do you calculate it?
Derivative of this.
The derivative of this, so now of this with respect to x1, and then the derivative of it with respect to x2, and the derivative of this with respect to, and then with its x. So what do you get?
1, 0, 0, 1.
So derivative this with respect to x1 is 1, with respect to, is it this one or that one? It won't matter, because actually the Hessian is symmetric. Okay? Okay. And this is something you should know. I don't remember the name of it, but if you take partial differentiation of a function with respect to xi and then with respect to xj, it's the same as taking with respect to xj and then xi. I don't remember. It has I think it was Cauchy's something. I don't remember exactly. So it's actually all symmetric. And the second function with respect to x2 means I have x2 here. Make sense?
Hessian will always come out to be symmetric.
It's always symmetric, yes, because of this.
Hessian of this case only.
No, of any function.
Whatever the power of x2 and power of x1.
Check it up.
Are you
I'm saying yes. The Hessian is always symmetric, yes. But check it. Try to.
In another course, we were optimizing a function over here. Hessian were sometimes symmetric, sometimes they were not symmetric.
Let's look at it. Let's discuss.
Maybe it doesn't matter the order because whatever we're organizing as row tuples or column tuples. That's why, but not
No,
symmetric.
because we are taking that x1 and x2 as a row, and still it would come out. I think doctor
Yeah,
is right.
maybe rows or maybe columns. So columns
I'm
or
saying
rows.
it doesn't matter whichever function is over there, whether it's a
The ij component. So that's aside here. So the Hessian, okay, at v as a function of x. This is a matrix, which means I can look at the ij component. It is defined as partial v by partial xi, and then xj. So that's the second derivative, right?
Yeah.
What I'm saying about this, I don't remember really its name, but something.
I know you can switch.
This is equal to.
Switching its place.
So there is a theorem that says this is equal to xj partial xi, and thus this is equal to the ji component of the same matrix. And a matrix that you have ij is equal to ji is actually equivalent to saying that this is the transpose is equal to this is matrix equal to its transpose, which means that it's symmetric. So double check that with ChatGPT, and yeah, okay, do check it, okay, and tell me which course that is, okay. So this is the Hessian, and what about the eigenvalues of this Hessian?
1 and 1.
1 and 1. What's the easiest way to look at it?
Diagonal.
The diagonal, right? When you have a diagonal matrix, the eigenvalue is R the diagonal, right? So it's just 1 and 1. So it's positive definite. So this is
Yes, positive.
positive definite, and thus this is. So that's actually the conclusion. Let me write it in a different color. So the conclusion is that you see the symbol here. This is how it looks like, while this one is the normal one that you have. Okay, so this is the normal greater than, but this is the curly one. Make sense?
So we can say then this is stable.
Yeah. No,
What is stable?
Not yet.
No, this is positive definite.
Not yet.
What is stable?
Petroleum box.
Did we even do Lyapunov?
No.
I'm just giving you a function, telling you check whether it's stable or not. Sorry, whether it's positive definite or not. I did not, take the time derivative of it, because to calculate the v dot, what is missing here?
The x dot.
The function, the dynamics itself. What kind of system we're talking about?
Yeah.
So this means actually I can take the same function and I can evaluate it around an infinite number of systems, right? I can try the same function with x dot is equal to manipulator dynamics, x dot is equal to mass spring damper system, x dot is equal to a satellite, and so on and so forth.
I have checked that. It says that if the continuous, only then it will be symmetrical.
Second derivative is always
Continuous.
okay. And then the first thing we said about v was
C infinity.
c infinity. That was an assumption. We said it's a smooth function. Thus we get it.
And that theorem name was Cloriot.
Who?
Cloriot.
Cloriot?
Yeah, Cloriot theorem. You were saying that.
Okay.
The theorem you were mentioning.
Cloriot.
Yeah, Cloriot.
Cloriot? Doesn't ring a bell.
Or Schwarz.
Schwarz. That's
It
the
has
word.
both names.
Yes.
Cloriot and Schwarz.
Schwarz inequality or Schwarz theory. Yeah, exactly. The Schwarz is the one I know. The Cloriot, maybe historians usually go back and try to see,
I also did.
Okay, yeah. So, but that's the one I know. Makes sense? Easy. Another example. So that's example 1. Example 2, or example B. And the first part is that I'll give you x is equal to x1, x2, and x3. And I give you a function given by half x1 squared, half x3 squared. And the question is it around, again, the origin? Is it positive definite around the origin? Positive definite?
There is no x2.
There is, yes, not a x2 is part of the state space, but it's not appearing in the function.
So it's semi-definite.
Who said this is positive definite? So go back to the the intuitive definition where you say that it's 0 at x star and positive everywhere else. Is that the case?
It is, but
It's also 0 at x.
It's also 0 at
every
x2 equal what?
0.
every
Equal everything else. So if I put here x2 equal to 10, what do I get? Sorry, and x1 is 0 and x3 is 0. I get v is 0. If I give you another if I give you any value of x2, you're always gonna get, and of course x1 and x3 are 0. You always get v is 0. Is that the definition of a positive definite?
Positive semi-definite.
It's a definition of a positive semi-definite. So now just from this check, you can actually see that this is positive semi-definite. If you do the way that we did with the Hessian, you can actually calculate that the Hessian, and I leave this for you, okay, as a homework, but it's actually trivial. It's simply gonna be 1, 0, 1. Which means that the eigenvalues are 1, 0, and 1. Which means it has an eigenvalue at 0. So it's semi-definite. Make sense? By the way, the two examples actually I give you, they're actually they are a special case of a more generic case, which is if you have in general x in Rn, and you have a quadratic function given by this. So you see here, I'm not saying that v is approximately a quadratic function given by the Hessian. It actually is a quadratic function. This actually case, it is a quadratic function. The Hessian is actually the same matrix that you multiply by x transpose x. And if you go back to the other example, half x1 squared and x2 squared, it was actually, there was like some identity in between. So actually, here in the first case, so this, in example A, P actually was the identity in 2. And in the second case, the P is actually given by this matrix 1, 0, 1. And the rest are zeros. Okay? So actually from here, if you always have a function that looks like this, what is the easy way to check whether it's positive definite or not? Look at the eigenvalues of the P, the matrix that appears there. Okay, yeah. Which is the Hessian. So if I calculate this expression, the Hessian is the P. Okay, so always quadratic functions, when you write it in this way, the matrix that appears in between is actually the Hessian of the function, but not approximately. It's exactly the function. Yeah. What?
Why is it I of 2?
I2
Because we had x1 and x2 in the first example.
And second we have 1, 0, 1. So over there it's 3.
It's 3 dimension, but this is the matrix. 1, 0, 1, and the rest are zeros.
So if we have 4, then it will be.
If it's 4 dimension, yes, of course. So here P is actually n by n. Okay? And the positive definite of this is actually the same as the positive definite of this matrix. Okay? Make sense? Okay, another example. 2D. Still have time. So x is equal to theta and theta dot. Which example do you think this will be? What is theta and theta dot? We'll describe the pendulum, right? The pendulum example. So the v of x I'm going to be choosing here is given by, it's a very particular one. It's half theta dot squared plus 1 minus cosine theta. Does this ring a bell for any one? What kind of function this is?
This is the dynamics
What dynamics?
of the second order. Q double dot.
What does this term remind you of in a pendulum?
This is the potential energy of
This is the potential energy?
sorry, the
Kinetic energy. And this is
The potential.
potential energy of the pendulum. Okay. So what is the V here?
The potential.
Is it potential or
energy?
This is potential energy, gravitational potential energy.
Yeah, gravitation.
Gravitational potential energy, sorry. And this is the kinetic energy. So what is the V here? Total energy of the system, exactly. Total energy of the system, of the pendulum. And we're going to come back to the pendulum later. But let's take just this function and let's see whether it's actually locally positive definite or not. Okay? So, again, the gradient is
first one will be theta dot.
sine theta.
Sine theta, yeah.
Make sense? So differentiation of this function with respect to
Theta
theta is
minus theta. Sine.
sine.
Correct.
Make sense?
Yes, yes.
Differentiation of it with respect to theta dot is
Theta dot.
Yeah.
Hessian.
This is minus the cosine.
So I have minus cosine, exactly.
No, it's minus. It's cosine.
Cosine, yeah, exactly.
0.
0. Symmetric.
1.
1. So eigenvalues.
Cosine theta. Cosine theta.
Is this the matrix we should evaluate?
No.
Why?
Evaluated at the start.
Absolutely. It should be evaluated at the equilibrium point you want to talk about. The pendulum had 2 equilibrium points, remember? It had the 0 and 0, which is the downward position of the pendulum. And it had the upward position of the pendulum, which was pi and 0. Because the theta itself, so the state space was from minus pi to pi included cross R. So if I evaluate the cosine 0, what do I get? 1. 1, 0, 0, 1, positive definite. Locally or globally?
Locally.
Why?
Because it has two equilibrium points.
Because it has 2 equilibrium points. Done. It has already, the system itself has 2 equilibrium points. And it's actually easy to check. If I plug in here the state space, if I put here the pi, what do I get?
Minus 1.
Minus 1 and 1.
1 to 1. Yeah.
That's
Indefinite.
Is that correct even? So, in other words, so if I use this function to evaluate the equilibrium, so the positive definiteness, so in conclusion, the positive definiteness around, let's call this the x star 1, and this is x star 2, because it has 2 equilibrium points. So evaluate the positive definiteness of V around x star 1, what do I conclude? It's locally positive definite. Why locally? Because in the state space, okay, in the state space actually, it's only at that location. Okay, and also the Hessian here. So go back actually. So the correct way to say it is that is V equal to? Is this equal to half x transpose Hessian x? Approximately, exactly, because of the Taylor series. You see, the Hessian is not exactly equal to it. There are higher order terms that we eliminated, and thus actually this is approximately. And if this is positive definite, then the theorem says that
It is V is positive definite.
V is locally positive definite. I cannot say anything about the global behavior. I can only look at it locally. So the positive definite, this is locally positive definite. And if I try to evaluate around x star 2, I cannot say anything about it because it's indefinite. One is positive, one is negative. Make sense? Okay. Another example?
Doctor, can I have a question?
Yes.
And example, no, in B, I think.
Okay. No, B. Yeah,
Okay, there is no x2.
that's right.
So we say that it's a positive semi-definite.
It's positive semi-definite, yes.
So with no choice or with no possibility that it may be the other terms after the Hessian, the other partial terms may contribute to be positive.
Are there any other terms in this example?
No.
Why? Because it's exactly equal to this expression. It's a quadratic function.
So why here we say exactly?
Because this is not an approximate. This is not approximately equal to some quadratic form. It is a quadratic form.
Can you say this is? Can you say this is not C infinity?
No, it is C infinity.
It's not differentiable
Why?
to infinity.
Why?
It will give you-
After you get the zeros and you differentiate, what do you get?
This is 0, 0.
So you can differentiate it until you want. So it is a differential. Another question? Yes, Fahd.
V of x,
Which example?
anyone.
Okay.
Let's talk about number D.
Okay,
Do we always pick the energy equation?
next lecture. Do we always pick the energy equation? That's exactly what we do next.
That's the V of x.
It's easy.
Kind of confusing.
I know, exactly. How do we get it? Lyapunov died and did not tell us how. Okay, so we don't have no idea. The best thing that we can come up with is indeed the energy of the system. If I have a mechanical system, I already have a kinetic energy and potential energy, so why not use it?
Yeah, and
Stable.
So
a follow-up question would be why didn't we use a similar function to what we used before, like half theta squared plus half theta dot squared, for example?
so the quadratic form, you mean?
Yeah, exactly.
Okay, what? Use it, and that's you'll find. I would say I can easily say it's 99% of how people do control and use Lyapunov analysis. Just start with the quadratic function. If it works, it works.
Wouldn't it always be positive definite?
The function would be always positive definite, absolutely. So you don't even need to check for it. But what might happen
The hash.
Second derivative.
The derivative of it is
when you evaluate the derivative of it along the trajectories? You might not be able to show it is.
I'm talking about f of x.
I'm talking about the v dot
Ah, okay. Yeah, so as a result of f of x.
as a result of f. When you pair it with f of s, when you pair the gradient of it with f of x, you might not be able to show the nice stability properties that you want to do. And by the way, and this is next lecture, inshallah, the idea of showing the stability of a system is tightly coupled to deriving a controller. Okay?
Okay.
But that's for next lecture. Yes?
The reason for it being energy-like is because any stable system would naturally die down after some time, and energy would
That's an excellent intuition. Yes, absolutely. And thus,
it will be stable.
so next. That's an excellent intuition, yes. But that's exactly Lassalle's invariance principle again. Okay. Let's come back. So another example. Now let's shake things a little bit. Let's go to Rn. So this is part 2. Let's go to the case of Rn times n. I'll give you now a function of a state. The state is equal to m, which is an n by n matrix. So the function that eats a matrix and gives you a real number is defined as the trace of m transpose m.
Okay.
So it eats a function, it eats a matrix and gives you
scale.
a scalar. Does it satisfy the condition?
Yeah.
Okay, so it's a function, it's a scalar function. How can we show that this is positive definite
Yes.
around the origin again, which is the big matrix that has zeros?
Yes.
How?
Because it's the square of each diagonal matrix, summing with each other.
That's correct.
In terms of matrices, matrices, we can call it is a quadratic-like function.
Absolutely. This is the quadratic form of a function on matrices. Okay? And you can actually see it by a very nice identity. The identity state is as follows. So if I have the trace of A transpose B, where A and B are both n by n matrices, then actually this is equivalent to the vectorization of A. What is it? You remember what the vectorization was? You just take this matrix, rows and columns, and you make them into one big, vector. You take the vectorization of A, transpose it by the vectorization of B. Okay. So let's maybe call this small a transpose and small b, where small a is the vectorization of A, and this is the dimension of it is what? Dimension of it is what? N squared, absolutely. Yes?
Isn't the trace the summation of the diagonal?
That's right.
Right? So here when you did the vectorization, you're somewhat taking all of the components of the matrix and putting them into the result chain.
Yeah.
So, yeah, but in the trace, you only took the diagonal.
That's right. And we took the trace of the multiplication of them.
Okay.
Go back at home and check this for yourself. Take any matrix, generic matrix, do 3 by 3. If you have, stamina, you can go higher. Take the 3 by 3 and multiply by the 3 by 3 and see what happens. Okay? Check it for yourself. Okay? It's after lunch, after dinner. Okay? Any questions? So indeed, this is positive definite. Okay? Okay. Because it's actually nothing else than something that's A transpose B. Okay? So it's the same as, the function x transpose. Actually, this is like the same as vector. So let me call this M transpose M. So you see, it's exactly the same quadratic form. Okay?
So this is curly or
Sorry?
curly or just bigger than?
That's absolutely yes. That's just the normal one, yeah. Okay, positive definite. Make sense? I think, okay, last example of today. I had more stuff on the VDOT, but we'll leave this for next time. Okay. Actually, I'm going to put it in the homework. Okay, so assignment. Actually, I'll give you an assignment. Okay. So graded assignment, and then but it's really very easy. Okay, it's just after you calculate the hash, after you calculate the gradient, you just multiply by the x dot and so on. You're going to find there are a lot of examples, and it's really very easy. But the next example is actually very important, and it will show you something really different now. Now let's look at the last example is the case of SO3. What if I have the state to be a rotation matrix that lives in SO3? And I have a function of R that's given by the following expression. It is half trace I3 minus R. I3 here is the identity matrix in 3 dimensions. Minus R. Scalar function? Anything bothering you in it? I give it an R. What does it give me? Scalar. Okay? Make sense? So the question is this function, is V of R positive definite around the R equal to identity? If I plug in here R equal to identity, what do I get? So V of identity is equal to half of the trace of identity minus identity. What do I get? Trace of the zero matrix is 0. So it's a valid point. I can use it. Okay? So how to move on? So this is the kind of equations you're going to be working with if you want to do Lyapunov on SO3. Why is SO3 important?
Related to the
Right.
laws
Any robotic system has SO3 in it, one place or another. You're all playing around with SO3 now. Okay? Whether then the factor of the manipulator, or whether the configuration of the drone and so on. So this is very fundamental. And this function, we're going to come back to it. It's a very important one. Okay. So the trick is as follows. Okay. Rodriguez formula rings a bell. Anyone memorizes it? Or I can expand it as, first of all, there was something called the exponential coordinates, right, of SO3. And you remember when, if you given any r, I can go back and forth, okay, to some n hat and some theta, right? Which we call the exponential coordinates of it. And it was actually given by, so this was equal to the exponential of n tilde multiplied by theta, right? The exponential map of SO3. And we said that this exponential map has a closed form expression given by the Rodriguez formula, which is, in this notation, is equal to I plus sine theta. And I'm going to, for simplicity, I'm going to be doing shorthand notation for sine theta to be s theta, s sub theta multiplied by n tilde plus 1 minus cosine theta multiplied by n tilde square. Yeah. So that was the Rodriguez formula. Okay. So, and then if you plug in this expression in here, what do you get? So V of R, and you plug in that term, what do you get? You get the half of the trace. I3 minus this expression will be, the I goes with the I. This is an I in 3. So you get minus sine theta until the minus 1 minus cosine theta n tilde square. You all agree? The trace is a linear operator. What does a linear operator mean?
You can take everything out.
If I have a scalar, if I have a function of lambda multiplied by v1 plus v2, I can write it as lambda multiplied by f of v1 plus f of v2. This was the definition of a linear map, remember? And the trace is a linear map, which means I can rewrite this expression as half minus sine theta trace of n tilde. That's the first expression. And then I have minus half multiplied by 1 minus cosine theta. 1 minus cosine theta is just a number. It's a scalar. Right? Multiplied by the trace of n tilde squared. And now there is a homework for you to actually show that. It's very easy. Okay. You can actually show that the trace of the n tilde is always equal, so of any vector. So the trace, let me write it here. So you can prove, so that's actually proof for yourself at home. Prove that the trace for x in Rn and for x tilde in SO3, small SO3, so the skew-symmetric representation of this vector, for any vector, for all x, that the trace of x tilde is equal to 0. And that's actually an easy check. I'll show it to you right now. So 0, 0, 0, and there was some other stuff, right?
Yeah.
The trace is sum the diagonal. 0. Done.
Yes.
And the trace of x tilde square, so you multiply x tilde by x tilde square is x tilde multiplied by x tilde,
Yes.
as is. You can actually show that this is equal to minus 2, the norm of the vector squared.
Okay.
Minus 2 multiplied by the norm of the vector x squared. Now go back. You remember the n tilde, the n hat, had a norm of what? You won. It was a unit vector.
Yes, yes.
Which means that actually this is equal to minus 2.
Yeah.
So, which means that this is actually equal to 1 minus cosine theta. And the theta here goes from, lives where? From minus pi, not included, to pi included. If I plug in here theta, minus pi,
Minus pi is not included.
it's not included. If I plug in the pi,
Pi, that would be minus 1.
and then you get what is the V of R? 2. So V of R will be, the greatest value of it is 2 or equal, and the smallest one is?
No, 0.
لا, almost minus 2.
No. Cosine of something, cosine of an angle and cosine of that minus of the angle is always the same sign. You don't get a minus sign. The sign is the one that takes it. That changes the sign.
Yeah, yeah, yeah.
So sine of theta is equal to, so sine of minus theta is equal to minus sine of theta.
Yeah, yeah, yeah.
But cosine of minus theta is equal to cosine theta.
Yeah.
So the cosine does not matter about the positive and negative.
Yeah.
If you plug in the cosine of 0, what do you get? You get 1. So the smallest value is 0. Equal to 0. So is it positive definite?
It is positive semi-definite.
It's positive definite, 0 is included.
It's positive, absolutely. It's positive semi-definite, yes. So around this point, it's actually positive semi-definite. Okay? That's it? Okay, next time, inshallah, we're going to be looking at an extension of this, and then we're going to be starting control, finally. Okay?